Hello and welcome to Lean Consensus call number 1. Number 7. This is the first time that the calls are no longer branded after the Beam calls. It's been quite a while actually since we've had a call. It's been over 3 months. We haven't taken the summer off. I think we've been all working extremely hard, and today's call is to a large extent the product of all this hard work. So let me get started and share my slides. Okay, so the topic of today's call is the post-quantum signature specifications. And since the last call, we've introduced leanEthereum through the Ethereum Foundation blog. And leanEthereum basically has 3 constituent parts. It has a leanConsensus, which is the rebrand of the Beam chain. We have lean execution, which is all about snarkifying the L1 EVM, as well as potentially introducing a new ISA, RIS5, under the EVM. And there's a whole set of calls called the ETH-proof calls that are dedicated to lean execution. And then there's lean data, which is the next generation of data availability, in particular, making sure that it is post-quantum secure. This effort is still very, very nascent. We just have the name. We don't have anyone actively working on it, and we don't have any calls for it right now. If you're new to these calls, here's a few useful links. So we have the protocol calendar, we have the Discord where anyone can ask questions, as well as the YouTube where we have a bunch of recordings. And there's actually a lot more content on YouTube now because we have this new series of calls called the post-quantum Interop calls, where the goal is to try and spin up some post-quantum DevNets, and I believe we've already had 8 of those calls once per week that are on YouTube. And we also have a brand new URL replacing a Beam roadmap now that redirects to leanroadmap.org. And thank you so much to Unawat from the Ream team for maintaining this great website. So here's an overview of the 2025 schedule. So we already had the very first call where we introduced lots of teams that came forward interested in working on leanConsensus. We've had 5 different calls where we gave updates on various important topics related to leanConsensus. And then we had Beam Day in Cannes at EthCC, which was a great success, and it's also available on YouTube. There's maybe 6 or 7 hours of content there if you'd like to dig in. And one of the great outcomes of Beam Day was that we kind of came to rough consensus that a good next step would be to have a post-quantum DevNet as a good next step, and that led to the post-quantum Interop calls. So quite a bit of time has happened. A couple months has happened between Beam Day and today, and today is basically the first of a series of calls, which will be much more specific about what exactly we are building, and starting to look into the Python specifications as well. Now, initially, what I was hoping to do is to have a Beam week or leanConsensus week in November at DevConnect, but I won't be able to travel to DevConnect. So instead, I'm organizing a couple of events in Cambridge. So one is a post-quantum signatures workshop that will happen 4th to 6th, and there's also going to be a consensus layer architecture retreat for Ethereum Foundation researchers. And I'm hoping to be able to make a ton of progress there in the post-quantum workshop. Hopefully, make a lot of progress on the DevNet. And then, basically, what I'm hoping to do after the Cambridge workshops is to make a ton of progress on the various sub-specs. So for the peer-to-peer networking, for rainbow staking, the finality gadget, and then eventually, hopefully towards the end of this year, we will have the full leanConsensus specs, at least some sort of first draft potentially. And one thing that I'd like to highlight here is that there's a lot of excitement on some new ideas related to finality, and those will be discussed during the consensus layer architecture retreat. The Ethereum Foundation actually made a couple of hires very, very recently, and they're bringing in very interesting new perspectives that could lead to some modifications over 3SF, which was the latest and greatest that was known just a few months ago. Okay, so today's call is all about leanMultisig, which is the post-quantum signature, and you can think of it as having two constituent parts. You have the so-called leaf signatures, which are the signatures that the attesters produce when they sign, and then you have a step called aggregation, very similar to BLS, that will take all of these signatures and compress them into a very short multi-signature. So in the leaf signature, we have 4 layers of the stack, if you will. So there's the field that we start with called koala bear. And then once you have a field, you can define a hash function which is friendly to this field, which is snark friendly. And here we're suggesting to use Poseidon 2. And then we have what's called a one-time signature scheme, which is an optimized variant of Winternet. And then we have leanSig, which is an optimized version of XMSS. So that's the leaf signature part. And then the snark aggregation itself is made of constituent parts. We have the polynomial commitment scheme, and here we've been putting a lot of effort into where. We have a snark, which is an optimized variant of Superspartan, and then we have stuff which is essentially completely custom. So we have an ISA with 8 instructions, 4 opcodes and 4 precompiles. We'll learn much more about that shortly from Emile, and we'll also have basically a program that will do the aggregation, including the recursive aggregation of signatures, which again is also completely custom. And my hope is that the complexity of all of this is actually very, very much manageable, and specifically we can have the full verifier for these lean multisigs in under 1,000 lines of Python. And part of the reason why I'm so optimistic is that we can get there is because, for example, leanSnark, which I guess includes the PCS and includes all of this stuff, or at least this and this, was 400 and less than 500 lines of code. So yeah, I'm hopeful this is very manageable complexity. Here's a little bit of a cheat sheet on the performance very quickly. The pub key is about 50 bytes. The signature is about 3 kilobytes. Signing times on a single core and verification times are less than a millisecond, hundreds of microseconds. The number of hashes required to verify a signature, that's a leaf signature, is about 150. And the key generation process for every year of lifetime is about half an hour. So if you want to have a validator that lasts 10 years, for example, that will take about 5 hours. These are potentially non-optimized and might improve. And this is on I believe, a 10-core MacBook. And then on the aggregation side of things, what we're working towards is to aggregate 1,000 signatures per second. We're not there quite yet, but we have all sorts of ideas that we believe could get us there. And these are aggregation speeds on a CPU. So, for example, on a single MacBook CPU. And yeah, for GPU numbers, roughly speaking, you can multiply this by 10. So it would be 10,000 signatures per second on a single gaming GPU. And then the aggregate size for 128 bits of security is about 128 kilobytes, which is a nice coincidence in the numbers. Okay, so these are the speakers for today. We're going to have Will talk about some of the coordination around the Interop calls, as well as the Cambridge workshops. Felipe will talk about the specking template that he put in place with lots of good practices from other efforts, for example, the EOS project. Thomas will talk about leanSig, which he's already spec'd out. And we also have Emile, who will talk about the leanVM that he's actively working on. So yeah, Will, the floor is yours if you're ready.
Excellent, thanks. Okay, is that coming through?
Yes.
All right, great. So the first, I guess, PQ interop, like Justin mentioned, it's the first in a series of iterative feature-focused DevNets. So we're kind of working to like incrementally build up a new leanConsensus client, it's sort of one layer at a time, and really starting this whole effort with the post-quantum signature aggregation, which you'll learn a lot more about the details today. So really kind of like setting the stage by how are we balancing out all of these key variables, like the design of the PQ signature schemas, efficient networking, faster slots, 4-second slots, 3-slot finality, and then also kind of bootstrapping some of the infrastructure that's involved in a multi-client DevNet process. And so really trying to learn what we can from the ETH Panda ops, from the Steel team, protocol security, leaning in on metrics and things of that nature. So really all of this is sort of like trying to balance out all of these design variables, such as validator count. Justin was talking about the amount of time that it takes to generate the keys based off of lifetime. So looking at the file size, the key gen time, the lifetime, and trying to balance out all those variables, and then do this obviously in a multi-client environment. And so all the participants in this, we're kind of the first half of this year, like the Beam chain talks really gave us an opportunity to all start begin to formulate these relationships, and really the client teams that are emerging out of it as key participants and contributors are Ream and Zeem and Quadrivium. And then with this particular effort, we've got a lot of cryptography researchers from the EF and beyond, consensus researchers, networking researchers, and then people working on specifications, networking, things of that nature, and all trying to like advance this whole effort with a spirit of simplicity and optimality, which are core tenets of lean Ethereum. So Justin already directed you to, we also have a post-quantum, it started off as a Telegram group. Now we have the bridge bot. So we've added the channel to the ETH R&D. You're more than welcome to join both. We've got the calls, as Justin mentioned, every Wednesday at 2 p.m. UTC. Happy to see anyone there. We try to post the calls to YouTube immediately after. And then we kind of have this like sort of shadow fork of ACD emerging. We created a GitHub org so we can work without like causing distractions to like more timely Fusaka related shipping efforts and things of that nature. So we've got a lean Ethereum GitHub org. Within there, there's a couple of different repos. We've got a PM repo where we're starting to issue PM spec sheet, or sorry, DevNet spec sheets and meeting minutes. We also have a project board in there, so you can kind of see the efforts that are in flight, and then all of the specs and sub-specs that you'll learn about later on today. And as Justin mentioned, we've been really the last 2 months, we've gone through 8 of these calls every month or every week, starting very high level. The Zim and the Ream team kind of started off with their pitches on what they wanted out of this DevNet process, what our stretch goals were to get to, say, by November, and then trying to converge on some high level criteria for the DevNet, bringing in outside experts from ETH Panda Ops, Steel, Katya from Lodestar has been helping out a lot with this idea of really trying to be metrics forward, having client and agnostic metrics that we're able to measure. Starting to build up all of the infrastructure that we need, a fork of Dora, Genesis generator, things of that nature, and then working on some getting all the specs written. Pama has been really instrumental in that, along with all of the client teams. And yeah, we just finished DevNet 0 specification last week, which is great. We haven't launched DevNet 0 quite yet, but as Justin mentioned, we've got this Cambridge event coming up. So really kind of working to get the first DevNet 0 up and running before then, finalize DevNet 1 spec before then, and then use that IRL event to really take things to the next level. So yeah, there's already a lot of key objectives that we're targeting to get out of that workshop. And then there's some special topics. So looking into some additional research around cryptography, and then also trying to finalize the criteria and structure around the proximity prize, the $1 million effort that Justin announced recently. And I guess fear not, all of this will be recorded just like Beam Day was. So we'll make the effort to record what we can and get it transcribed and up on YouTube and notes shared.
Amazing. Thank you, Will. Any questions? So Dara is asking, given you're assuming go ahead.
Oh, yes. I said, so you're assuming that you have access to a quantum, post-quantum recursive proof system. So another approach rather than using XMSS would be to just prove knowledge of the private key. Have you considered the performance trade-offs of that, flexibility trade-offs? Because obviously, if you have a signature of knowledge, then you can prove anything else that you want to do at the same time. If you need more than one signature, you can do private aggregation.
Right. So this is actually, that was our starting point. So there's a project called Ziggy from Starkware where they do exactly this. And there's, I guess, 2 trade-offs. The first one is that the leaf signatures are bigger. So tens of kilobytes instead of 3 kilobytes. And more likely than not, bandwidth is actually our bottleneck. The other big trade-off is, actually there's 3 trade-offs. The other big trade-off is that the signing time grows quite a bit. So, we're talking about hundreds of microseconds on a single call. But if you're doing a proof of knowledge like Ziggy, it will take significantly longer. And one of the things that we want to do is be friendly to very weak devices. And by very weak, we have like very strong requirements. So the device that we have in mind as kind of the minimum barrier to entry is a Raspberry Pi Pico, which is a $7 piece of hardware. And so that's kind of fast enough to be able to generate those signatures in a single core. And then another advantage of going down XMSS has to do with security. So generally, the security analysis of proofs of knowledge are in the random oracle model, whereas here we have security in the standard model. And what we want is to have maximum security of the leaf signatures, because that's something that wouldn't change, hopefully ever.
I see.
Right?
Okay.
Whereas the aggregation, which is in the random oracle model, potentially could change.
Thank you.
Absolutely, great questions. Okay, next up we have Felipe, who will talk about the lean specification template that he created.
All right, let me try to share my screen. And can you see that okay?
Yes.
Great. So I'll try to just lay down some of the Python foundation for the specs, and then others here will talk about what we've done there so far. Let's see, there we go. So the repository structure for leanSpec is basically this. So we have the specifications tree with some type definitions that can be distributed, more generally across the subspecs as well. And in the subspecs directory, we have the subspecifications, and the tests have this nice mirrored tree where you can reference sort of the specification tests with the specification in a similar hierarchy, in a similar pattern. We have the documentation, and we have a PyProject TOML where it's basically a single source of configuration for the entire Python side of the project. A little high level overview of the setup that we have. We kept some pretty modern Python version support, so it's 3.12 and above, and 3.14 is scheduled for October. So we'll have to see if there's anything there. But since we are just getting started, I don't see any issues there. It's nice to have the more modern version, so we can keep some like syntax, more modern syntax support there. The tooling that we went with was a little inspired by some of the other specifications that, like the execution specs from part of the Steel team, as well as the testing side, the execution spec tests. So we used some of these tools, UV, Rough, Tox. A couple of these are all the ones on the screen there. A few of these are pretty standard for projects, but I'll talk a little bit about why we used some of the other tools in the next slides. Like I mentioned, PyProject TOML is where you could find most of the configuration. One of the exceptions is the Tox ini, where you can just configure commands for Tox, which is pretty standard for Python projects as well, if you're familiar. And a little bit about the typing. Currently, we have some very simple types defined with Pydantic, which is really nice. And I'll get a little into the Pydantic side as well. But Tama has been doing a really good job of defining some simple types there that are that live within the repository. But we have this goal of aligning types sort of across the specification repositories, at least some of the base types. And then the more specific types can just live inside the leanSpec. Why we went with UV, this is built with Rust. So it's much faster than some of the traditional tooling for Python projects. If you're familiar with pip or virtual environment creation, this does it much faster. It's an all-in-one replacement for pip and virtual environment managers. So it's quite nice. It leads to some simple, powerful commands, so you can just come in and start working on it. Like just UV sync all extras will build you a virtual environment. It'll install all your dependencies, and you're ready to go with this package. Rough is much the same way, also built with Rust, same team. The Astral team is doing some really nice work with Python tooling to make it faster. So because it's the same team, there's some seamless integration there. So these tools were borrowed from the Steel repos, and it's really nice to use. This is an all-in-one replacement for if you're used to Python projects. it bundles Flake 8 for linting, isort for importing, Black for code formatting. So it's really nice as well. It's much faster. You can also configure everything in the PyProject TOML, or if that ever grows too big, Rough has this nice way of specifying its own configuration file. A little bit of the development toolchain. Pydantic has been really nice for validating some of our data models. This proves also really nice on the JSON deserialization and serialization support. I will go into that a little bit and how that's helped in the other specification repositories and kind of why we chose to use it here. PyTest is the standard for testing. There's a lot of support and flexibility that the framework gives us, a robustness that's been around for a while. That's a no-brainer. And some of these are standard talks, MyPy, make docs for documentation, and spell checker just to keep some short PRs low. Pydantic. So this is kind of like the main focus for allowing data models to just have validation built into it. We don't really use the serialization just yet, but basically invalidated can't exist. And so you just get to focus on the code and the readability there. Pydantic is an entire library that does the validation, right? They have their own tests for this and they work really well. A good example of this is creating the strict base model, which Thomas has created. And this basically can make all your types immutable. You can forbid extra fields. So Pydantic also provides us some really nice configurations that we can just set for base types. And the JSON serialization really kind of comes into play when we start thinking about maybe filling test vectors for clients from the specs, from the Python code, and generating JSON objects from those, or filling our Python models from test vectors in cryptography libraries or from anywhere else for testing and within our repository as well. So this is just some really nice setup and a really good direction to head for Python types. And my suggestion here is that so borrowing again inspiration from what's been done right, I think in my opinion in the execution specs and the testing side. Pydantic with PyTest can provide us in the future eventually some of this really nice framework, this nice flow for possibly testing. So PyTest in itself is just the standard. It provides reusable fixtures and setups across tests, parameterization, built-in support for temp directories, mocking, exception testing, all of these nice bells and whistles. But at the same time, thinking ahead about clients consuming test vectors. What we've seen on this in the Steel side in the test repo is there's an extensive area to reach into with custom plugins and PyTest's extensive hooks that they have. And basically what East has done, the testing side is, and we can imagine something similar, some sort of, maybe even future testing scenario comes about, but defining custom plugins that can now, with the Pydantic models and JSON support, we can define test cases that will fill JSON test vectors and they run these expectations against the specifications. So they fill using the specifications. And then receiving that validated output, you can execute those against clients. And so this has been a really nice flow for them. I think it's a pattern that's worth exploring here eventually. And yeah, these can be used to consume generated fixtures for simulator interactions on Hive. You can execute them on live networks. So this is really a lot of flexibility and robustness that PyTest and Pydantic can provide. And yeah, and maybe flexibility for potential scenarios, exploring custom plugins. And that's sort of all I have on the project setup side of things. I'll stop sharing.
Amazing. Thank you so much, Felipe. Any questions, especially from the devs or the speckers? I mean, for my part, I'm really pleased that all of the best practices have been, or at least most of them, have been condensed in this template. And I think this is going to make a big difference relative to the beacon chain, where I think we made a lot of mistakes. And hopefully that will allow us to move significantly faster.
Yeah.
Thanks again, Felipe. Next up, we have Thomas, who will talk about the specking effort for leanSpec.
Yes, let me share my screen. Can you see my screen?
Yes.
Okay, so perfect. So hello everyone, my name is Thomas, and today I'm excited to present the leanMultisig specification. This is a general proposal for securing Ethereum future in a post-quantum world. So over the next about 40 minutes, we are going to walk through that vision that drives this work and the specific cryptographic elements we applied, some high performance component we have designed, and we can see that as a complete reimagination of the consensus layer, where simplicity and security are really important and the best practice to follow. So before we dive in the technical details of the specification, it's important to understand the high-level vision that motivates these works. So this is heavily based and inspired by the Justin Drake post on leanEthereum, which sets a very important mission for the next decade. So the vision can be splitted into two key modes. First, we have a defense mode that we can also call a fort mode. The goal here is absolute resilience. What does this mean? This means that Ethereum needs to be a bedrock for the future of finance and the Internet of Value. This means that it must survive anything like nation state, and most importantly for our talk of today, the threat of quantum computers. And second, we have the offense mode or beat mode. This is about extreme performance and massive scalability. So we are talking here about a future where thousands of transactions per second on the L1 and millions on the L2. The goal here is to make the on-chain experience really seamless for all the new billions of users. But the challenge here is, how do we achieve this beast mode performance without ever compromising the fourth security mode? This is a question that we are trying to answer here through all of the design choices we made and through all of these specifications. So first, let us talk about kind of the lean spirit that guided us through all of our choice and all of the specification design. So we try to translate this big vision into practical working code. We follow for this three core principles that define the lean spirit. First, maximum simplicity. Every component is designed to be as minimal and clean as possible. Complexity is kind of the enemy of security, especially in cryptography. And by keeping the design very simple, we reduce the attack surface and make formal verification of the system correctness much more achievable. Second, we have next-gen cryptography. We are trying to move away from legacy crypto and building a unified hash-based foundation. This approach is powerful because it simultaneously addresses two of the biggest trends in our space. First, the rise of snarks, and second, the looming quantum threat. In third, we have hardened security. We try to bring to Ethereum there a conservative security model. We try to rely on the simplest, most well-understood cryptographic assumption proven in the standard model where possible. We avoid complex or exotic assumptions wherever this is possible. And these three principles guide every decision we make in the spec. So now let us focus on the first major challenge that this spec directly solves: signature aggregation in a post-quantum world. The problem is the quantum threat. Ethereum current consensus relies on BLS signature. They are super cool and fantastic for aggregation, but their security is based on elliptic curve. And we know that elliptic curves are vulnerable to attacks from future quantum computer. So this is kind of, we can call that a ticking clock for Ethereum long-term security. We don't know when this will happen, but we know that this will happen at some point, and so we need to be prepared. So the alternative is a hash-based signature or even lattice-based. A lot of options have been studied, but we retain specifically the XMSS signature scheme that was designed by the Ethereum cryptography team, especially by Benedict and Dimitri from our team. And the security of this XMSS signature scheme relies only on the property of a secure hash function. And this is very important because this is a simple and secure assumption, making it resistant to quantum attacks. For now, it's our best candidate for a replacement. But of course, this comes with some issues and scalability challenge. Unlike BLS, individual XMSS signatures are large and computationally expensive to verify. We can't just have every validator post their own XMSS signature on-chain. It would be far too slow and costly. This means that aggregation is essential, and we need a way to compress thousands of signatures into a single small proof. And to handle the scale of Ethereum, this system must support recursion. That means the ability to combine existing proof into a new one. This is the core problem we set out to solve. So to build this post-quantum system, our specification is built on three core cryptographic ingredients that are listed into this slide. Each one is carefully chosen to work perfectly in harmony with the others. First, we have a prime field, koala bear. This is, we can say, the mathematical universe where all of our operations take place. It's a 31-bit field specifically engineered for performance. As we will see, it is optimized for both fast Fourier transform and our chosen hash function, which is Poseidon 2. Secondly, we have the hash function, Poseidon 2. We can't really use a standard hash function like SHA-3 or Blake. We need a zk-friendly hash function designed for algebraic circuits, and I will explain afterward why this is very important. Poseidon 2 is the state-of-the-art designed to minimize the number of constraints needed in a stack, which directly translate into faster proofs. And finally, we have like the big PC, the signature scheme, XMSS signature scheme. This is a hash-based stateful signature scheme that provides the post-quantum security for individual validator attestations. So then the rest of our talk will be a deep dive into each of these ingredients, starting from the ground up with prime field. So let's start at the absolute foundation. All of our cryptography is built on top of the structure that we call a prime field. For anyone that is not familiar, a prime field is a finite set of numbers that use clock math, or we can also call that modular arithmetic. As you can see in the diagram on this slide, when you go past the large numbers that is a prime, you just wrap around. This creates a closed, predictable mathematical universe. This property is absolutely essential for building cryptographic systems, especially for the snarks that we use to aggregate signatures. But not just any prime field could work. We use a specifically engineered 31-bit field called koala bear. This was chosen for three key properties that make it perfect for our global proving stack. First, and most critically for our snarks, it has a high two-adicity of 24. This is a mathematical property that means that the number p minus 1, p being the prime, has a very large factor of 2. This structure is essential for running fast Fourier transform, which are in some sort the algorithmic engine inside modern snarks. You can find FFTs everywhere in modern snarks. So, in summary, high two-adicity means factor-proof in some sort. Second, the cube map is an automorphism. This may sound a bit abstract, but it's a perfect handshake with our hash function Poseidon2. This is what you have to remember. And inside, Poseidon2 uses the x to x to the power 3 operation for the non-linear speculative layer, what we call S-box, and we will see later what S-box is. And because this is an automorphism in our field, this operation is incredibly efficient and algebraically clean, which again leads to faster and simpler proof. So always more performance. And finally, Koala Bear is a small field. It's a 31 prime field as opposed to larger field like 64 or even larger field for efficient computation on modern hardware, where we can apply very nice trick to make very efficient arithmetic between fields. And its size allows also for fewer rounds in the Poseidon permutation, further boosting performance for this hash. Every property of this field was chosen for a reason, as you can see. Then let us start.
Thomas, we have a question from Dara asking, is too high two-adicity important for small fields versus large fields?
Yeah, they are. Yeah, the two-adicity is important. This is always a compromise between the size of the field, the two-adicity, and all of the property. But for the small field, for the 31-bit field, we had to choose between Baby Bear and Koala Bear, and Baby Bear has less two-adicity, so this is very nice for that.
Okay.
So let us dive into the spec right now and for the FP class. So let's look at how we translate this mathematical field into a practical and safe Python implementation. For this, we use the pedantic library that was presented just before by Felipe to create our FP class. First, it's robust and safe. By inheriting from the base model, we can have an automatic validation. And the class ensures that any FP must hold a value within the correct mathematical range, that is between 0 and p being the prime. This prevents a whole class of bugs from ever happening. Second, our field elements are immutable, thanks to the frozen true element right there that you can see here. Configuration means that once you create a field element, its value can never be changed. This is a crucial feature for writing predictable and secure cryptographic code, so you cannot change the field by mistake. This is, let us say, additional security. This is a kind of an important feature to write, test, and everything safely. Finally, like the field validators there, this is a decorator that is quite important because it acts as a gatekeeper, meaning that no matter what integer you pass to create an FP element, it is automatically reduced modulo p before it's even created. You can't accidentally create an invalid element. In short, the implementation is designed to be as simple and safe as possible for the developer, handling the complex cryptographic rules behind the scene. In our Python spec, we make this advanced maths feel natural and safe for developers. So as you can see there, we have a summary of arithmetic operation and the FP class, which represent a field element, overloads all of the standard Python arithmetic operators. So you can add, subtract, multiply and divide this cryptographic object just like you will do with regular numbers. You have overloading for all of the operation right there on the right. The implementation so handle all of the complex modular arithmetic for you, including division, for example, which is done by multiplying by the modular inverse. This is kind of encapsulate complexity. For those who are quite familiar with more performant implementation like Plonky 3, this should sound a bit short for modular arithmetic operation, but here performance is not the objective. We just want a very simple spec without any performance consideration. So of course, if you want performance, you can add any source of trick and different algorithm to make this operation fast and using even SIMD instruction or anything, but this is not the goal there. And we include also another practical optimization when we generated upfront a list of 2 ADIC generators. In some sort, these are special fields elements that are required to run the FFTs. Instead of calculating them on the fly, which can be quite slow, this spec provides a direct lookup table. So as you can see there inside this function is a O1 complexity because this is just an array lookup. Now for our second ingredient, this is the hash function. As I mentioned, we use Poseidon 2 because Poseidon 2 is ZK friendly. Its main goal is to be cheap inside the ZK circuit. Traditional hashes like SHA-3 or Blake are very fast on a CPU, much faster than Poseidon, but creates millions of constraints in a snark. Poseidon 2 creates very few, which means faster proving time and smaller, cheaper proof. It's an evolution of the original Poseidon with optimized linear layers that make it much faster. As you can see there on the right, using the scheme, especially this one, it follows the Hades philosophy, which you can see in these ones. It is a mix of expensive full round that you can see there on the top and there on the bottom, where every part of the state is mixed. Here you have the S box right there, and you can see that for both of these full round, all of the part of the state are transformed. And in the middle, we have cheap partial round, where only one element is transformed. As you can see there, only a single element is transformed and not the other ones. So this provides the necessary security against both statistical and algebraic attack at a fraction of the computational cost when compared to Poseidon 1. And as we discussed, at its core, like the S box right there, is using the x to the power 3, which is a perfect match for the property of our Koala-Bear field. Now, let's look at the building blocks for Poseidon 2 permutation. First, we have the state. This is we can see that as the internal memory of the hash function, represented as a list of Koala-Bear field elements. The size of these states, or the width, determine the security and the throughput of the hash. Our spec provides optimized parameters for a width of 16 and 24, which are the 2 widths used in production and all over the place in our XMSS signature scheme and in our proof system. Second, we have the S box that we have seen in the previous slide. This is a nonlinear layer and the core source of the hash function security. As we established, our spec uses a high efficient cube map, which is a perfect fit for the Koala-Bear field. And third, we have the linear layer. The linear layer, this provides diffusion, meaning that they mix the state so that a change in a single input bit affects the entire output. The key innovation in Poseidon 2 compared to Poseidon 1 is that it uses 2 different highly optimized linear layers for maximal speed. Let us see these 2 linear layers. First, we have the external layer used during the full rounds of the permutation. Its purpose is maximal diffusion. It's built from a strong 4x4 MDS matrix and ensures that the state is mixed at the beginning and at the end of the process. Remember that we have these full rounds at the beginning and the end of the process. It's strong but more computationally intensive. And in the middle, we have the internal layer that is used during the many partial round and is designed for one thing, for speed. It provides fast and lightweight diffusion. Its structure allowed to be applied in linear time instead of quadratic time, which is a massive performance gain, making Poseidon 2 faster than Poseidon 1. Now, I will present you like the permute function. The permute function in our Spec is a public-facing API for the user. So the user for the hash function Poseidon 2 should only use the permute function, and all of the internal call are hidden inside this function. This is the only function that should be used by the user. So this orchestrates the entire process following the design strategies that I just mentioned before. I will detail how it works. So it starts with an initial layer. On the right, you can see here this initial layer right there with comment to explain you how it works. This prevents certain algebraic attack. Then it runs a few full rounds right there using the strong external layer and applying the S-box to the entire state. This provides the initial robust mixing. As you can see on this precise line, I know this is a bit small, but there the S-box is applied for S in state, meaning for all of the elements of the state. Next, we have the many partial round where the S-box is only applied to the first element of the state. This is, let us say, the cheap internal layer used for diffusion. This is where we have the optimization. And as you can see there in this line, the S-box is just applied to the first element of the state, state 0, and not to all of the elements of the state as it was done for the previous one. And finally, we conclude with another set of full round to ensure that the output is completed and securely mixed. And here, once again, like the S-box strategy is applied to all of the elements of the state. So this global strategy gives us the security of a complex permutation at a fraction of the computational cost when compared to Poseidon 1. I wanted also to make everything flexible and safe. So the spec for Poseidon 2 parent, because we have like a set of parameters to define any permutation, uses pedantic model and the class, all of the configuration for a given instance. For example, the width or the number of full round and partial round. Crucially, it also holds the pre-computed constants needed for the permutation, and it includes right there a validator that automatically checks if the length of this constant list match the expected configuration. So this is an automatic check, and that is very useful because it prevents any source of bug. Okay, so now we have our fast field and our fast hash function. Now we can finally talk about the main event of this talk, the XMSS signature scheme that is built on top of them. What is exactly XMSS? As we had discussed, it's a hash-based post-quantum secure function. Its security relies only on our hash function Poseidon 2, not on the complex math problem that quantum computer can break. It is stateful by design, meaning that each signature is tied to a specific time or epoch. This sounds like a limitation maybe, but actually, if you think about it, this is perfect for proof of stake because validators have a naturally sequential job of signing block one after the other. And so this removes the risk of key reuse and allows for a much simpler and more efficient design for the signature scheme. So at its core, XMSS is a nice way to get many time signature from one time secret. And we will see how this works precisely. If you are a visual person, I have put like a diagram right there that I will detail. So the scheme is built from two simple hash-based components. First, we have winternitz one-time signature. This is a very simple signature based on hash chain. As the name implies, it's only secure to use once. If you look at there, you have all of these hash chains right there. And at the bottom of them, you have all of the secret key in red. So, and how do we sign multiple times now? This is where the second ingredient comes in, the Merkle tree, that you can see there on the top. A Merkle tree is used as an aggregator. A validator generates thousands of winternitz key pairs in advance, one for each future slot they will sign, and then they place the public keys of this one-time signature as the leaves of the Merkle tree right there in blue, and publish the three single roots as their long-term public key in blue at the top right there. This root is very important because you will see later that the verifier will need to know this root to be able to verify a message. So if I recap on this nice diagram, at the bottom in red, you have all of the secret key, and you have a certain number of hash in the chains. At the top of them, after hashing the secret key a certain number of times, you have the associated public key. Then you hash all of the corresponding public key together to form the leaves of the Merkle tree. And then you do your classical Merkle tree. And at the end, you have a final global public key that is the root of your Merkle tree. And here you can see that, to summarize, if you want to sign any message, you first encode it. We don't need to know what it is right now, but as a function of your encoding, you will have to hash a certain number of times each chain. And in green there, you end up with a signature. And to verify this signature, you will have to rehash each element of the chain up to the given public key. And then the verifier will reconstruct the final Merkle tree to compare the roots. This is the basic of the signing, but what you have to retain is these hash chains at the bottom and in the Merkle tree. This is what is important for our spec. So now we will explore the three main elements of the public API, and the first one is the key generation process using the keygen function. So this formalizes the setup. First, it generates the master secrets, a random PRF key and a public parameter. This PRF key is the single root secret that everything else is derived from. So all of your one-time secret key will be derived from this PRF. This is the first step that you can see right there in the Python, in the pseudo Python. Then for each epoch, the key will be active, and a one-time key will be derived using the PRF. Then we build the Merkle tree over the public parts, as you have seen in the diagram before, of this one-time key. And the root becomes the main component of the public key. So here I have pointed out these Merkle tree things. And finally, you bundle everything together to form like a public key and secret key object ready for signing, right there. There, I wanted just to briefly mention a new innovation that just came out through a new paper of Benedict and Dimitri, because one of the major bottlenecks in hash-based signature is the verification cost, meaning that the number of hashes the verifier has to compute to go from the message, the signature, to the public keys. Our spec includes a novel optimization to address this called top of the hypercube encoding. The problem with traditional methods is that they can produce signatures that are slow to verify due to a huge number of hash to be done by the verifier. The insight here is that instead of allowing any valid signature, we can force the signature to be chosen from a small, predefined set of highly efficient regions. This algorithm takes a message hash and deterministically maps it to a signature format that required the fewest possible operation to verify. The result is a 20 to 50% reduction in verification cost with no loss of security and no increase in signature size. This is a huge win for on-chain efficiency. If you are a visual person, on the right, I put a small diagram where you have all of these hash chains. And as you can see on the right, we can have a mental model of this as an hypercube. And the more you go on the top of the hypercube, the less the verifier has to do as a job. That means the top of the hypercube, meaning less hashes to do by the verifier. And so the target is to go on the top of the hypercube. Of course, there are outsource of trick and concerns and security stuff, but you can have this mental model. Then let us go to the sign process. So the sign function puts all the pieces together. First, it needs to find a valid encoding. The signer repeatedly hashes the message with a new randomness each time row until the output lands in the efficient top of the hypercube region. This is the loop defined there. So you have a max try, and up to this max try, the signer will try again and again and again to encode the message to be in this valid region. Then we create the one-time signature based on this valid encoding. This is the job that is done right there in this big loop using what we call the code word. This is a valid encoding of the message. Then it generates the Merkle pass. That is what you can see right there. And this Merkle pass will be directly given to the verifier for him to be able to reconstruct the full Merkle tree and to be able to check the final root. And finally, everything is assembled together into a signature object at the very end there, containing the Merkle pass, the randomness row, and the hashes. This is a single signature object ready for verification. And finally, we have the third function that is part of the public API. This is the verification function. This is, let us say, the most important one because this is the one that will be used in our snark system because all of the aggregators that will want to aggregate signature together to form a single proof to put on chain will use this verification to verify again and again all of the keys. So verification is the reverse process in some sort and is fully deterministic. First, the verifier reuse the randomness row from the signature right there to recompute the code word. So the code word is recomputed right there. Second, it recomputes the one-time public key by completing all of the hash chains, remember the previous diagram, from the intermediate value provided in the signature. Then they hash this reconstructed key to recompute the Merkle leaf. And finally, as the Merkle pass was provided by the signer, we can reconstruct the full Merkle tree. And the final check is very simple. The signature is valid if and only if the candidate root that is obtained at the end of the hashes matches the root in the public key. This is the final check that you can see there when the Merkle tree.verify pass is called. This is just at the end a Boolean, true or false, that determines if the verifying function succeeds or not. Now, to wrap up our deep dive into XMSS, let's look at how the spec organizes all of these components into clean and safe data structure. Here, I only wanted to point it out the main object, let us say. So we have first the public key. This is the public-facing identity of the signer. It's very small, containing just the Merkle root and the public parameter. We have the secret key, containing all of the private material, and most importantly, the master pref key from what everything else will be derived, and the pre-computed Merkle tree. Of course, all of that must be kept secret. This is the secret key. We have the signature object, that is the one, the object produced by the sign function. It bundles everything a verifier needs to know to verify the signature. This is a class that you can see on the right. And finally, you have the XMSS config object that gives you all of the constant and parameters for a given preset. We have a prod config, but this prod config contains large constants, and so the key generation will take a huge amount of time to generate the keys and everything. And so we have also a test config where the parameters are much smaller for you to run unit tests or to play with it. Finally, so we have designed a highly optimized post-quantum signature scheme with a clean specification. We try to do so. But how do we know that everything is actually correct? The final part of what I called at the beginning the lean spirit is the commitment to rigorous testing. And I want here briefly to touch on with two very simple slides. So our testing philosophy is built on four core principles to ensure every layer of the spec is solid. First, this is very basic, but unit test. Every single function and class is tested completely in isolation to ensure that it behaves completely as expected. Second, we have a lot of round-trip integrity tests. This is quite easy to do with a lot of cryptographic components, but we constantly test that inverse operation work perfectly. This applies, for example, to an encoding, decoding things, or to the entire key gen, sign, and verify a life cycle. If you sign something, you must be able to verify. So third, we have some known answer tests for critical crypto primitives like Poseidon 2 permutation. We test against pre-computed test vectors using Plonky 3, for example, that is an existing audited library. So we know how to compute expected value from there. This ensures that our implementation is correct and protects against any future code change that may accidentally introduce bug. And finally, robustness and security. I have tried to not just test only the happy path, but explicitly check that our code fail as expected under any invalid inputs or anything. But of course, all of that could be improved with time. And here on the right, you can see like a full round-trip test for the signature precisely. So at the beginning, we generate some key, then we sign and verify a message, and we test also to verify an invalid message. And we try to check if the verification is as expected. And we do this test with a bunch of different configurations to ensure that we are not just lucky and everything works perfectly. So this philosophy is put into practice using a clear and modular test structure built on the PyTest framework, as mentioned previously by Felipe. We have a modular test suite with a dedicated test file for each cryptographic component, and this is also valid outside of the cryptography. We are trying to have a single test file for each component. This keeps our tests organized and easily to maintain. We use parameterization for coverage to efficiently run the same logic against many different configurations without duplicating code. This is, for example, what you can see there on the right. To test the correctness of the round-trip test, we run under a bunch of configuration with the lifetime starting at 0 epoch and then with the lifetime starting later. And we try to find different configurations that can be challenging for the code. For most of our complex and optimized algorithm, like for example, the hypercube encoding, we perform validation against some reference model and other implementation against in other correct mathematical implementation to check between two of them. And finally, we combine everything with end-to-end scenario to simulate real-world usage and what the user will do. So finally, to wrap up around everything, the leanMultisig specification kind of represents like a holistic approach to secure Ethereum. So we tried to build in using the lean principle of simplicity and security. And for now, it solves the post-quantum signature challenge, but in the future, we will add also other elements of the stack, such as like our full proving system, including the PIOP, the minimal zkVM, as well as the PCS and any other components that should make the leanConsensus done to the end. So thank you very much, and I will now be happy to answer any of your questions.
Thank you, Thomas. Fantastic presentation. One question that we have from Divya is, wouldn't it be better to also have property-based testing since we're dealing with specifications that have invariance?
What do you mean exactly by this question?
Oh, can I speak?
Yes, of course.
Yeah.
Sure. I meant since we have specifications that have certain invariants, like an hypercube that is defined in a specific way, wouldn't it be better to test that specification against a property that it should satisfy? So I sent the hypothesis a package where you can define a particular property, say a hypercube should have a particular property, and then you can sort of test it. And then you don't have to sort of build a number of unit tests, instead one property that will be valid for any amount of input.
We have also this unit test, and we are working to improve that, but we already have this kind of unit test. For example, for the hypercube, we have a specific file where we have some kind of small unit test, but as you just mentioned, we have also some tests that specifically test the properties of the hypercube, so that, for example, I say completely random thing, but for example, the sum of this array should be that or should be that, and we have such tests. But of course, all what I have described is very new, and so we are working very hard to improve that. Also, I forgot to mention during my presentation, but through the work of Emile, we recently discovered that maybe the top of the hypercube encoding system is not the most snark friendly, and this encoding may change in the future. This is only a piece of the signature scheme, and we can change it quite easily. So maybe this will not be the final encoding scheme.
Okay, thank you.
Oh, a snark optimization problem. I'll get my teeth into that.
Yay,
Sorry.
we'd love to have you,
Yep.
Daira. Felipe gave a thumbs up to Hypothesis, which seems to be a specific repo that Divya linked to. So I guess we'll have a look into that. One question from Partha is, what's the correct way to represent a public key if its size is 50 bytes? And I guess what he's getting at here is that it's not a multiple of 60, it's not a power of 2. And I guess one thing we could do for efficiency is to put a bunch of the flags and the kind of other validator information and concatenate it with the 50 bytes so that you get 64 bytes, for example. So when you register as a validator, one of the things that we're looking to do in the context of rainbow staking is to have multiple roles. So you could have the attester role, the proposer role, and the includer role. And for each, there would be a bit that you can set to true or false. And if you want to have delegations, there would be bits. And if you want to accept delegations, there would also be bits. So there's all sorts of metadata that we could squeeze in the 50 bytes. But I guess for now, we could just have an SSZ object, which is a list of 50 bytes, and it would implicitly be padded with zeros, I guess.
Yeah, for now, at least in the Python spec, we didn't handle anything with any optimization of this sort. We just represent it very simply, like the public key as the root plus the random parameter, let us say. And so this is just a list of finite field elements, and then we can just SSZ this list, but we can do any source of optimization, of course.
So if I'm understanding the top of the hypercube optimization, it's basically finding a point in the hypercube to encode a message that gives you a constant number of valuations rather than a variable number as in original XMSS, right? And so the SNARK optimization problem is basically routing the inputs and outputs of the hash functions correctly, given that you have a fixed number of hashes. Is that right?
It's mostly mapping a hash output into into a point in the particular hypercube layer more or less uniformly. And the problem is that kind of this number of points in a particular layer is not particularly nice number. And when you snarkify this process, which point you end up to, you have to deal with kind of long integers, not particularly long, like 130 bit or something, but still it requires some machinery like table lookups as well. For example, if you have tables, then it's not so hard. If you don't have tables, as we kind of the plan for minimal ISA, then it's more challenging.
You might be able to kind of tailor it to the koala bear field. I have to think about it. Yeah,
I think that also Emile will, just in the presentation just after, Emile will talk about the zkVM, and I am sure that he will kind of mention this challenge. But yeah, I think my understanding is that for now, at least in the minimal zkVM, we started with the basic encoding, so no hypercube things for now, but Emile will be able to answer this question.
Okay, thanks.
So removing the checksum is an optimization that was known ahead of this paper. This paper comes up with kind of this, in some sense, cooler and more subtle optimization, which has to do with...
Yes, yeah.
Okay, nice. Oh, actually, one point that I didn't mention when you asked your first question, Dara, was another very nice property of XMSS is that you don't have side channel attacks that could leak the private key. So because you're dealing with one-time signatures, it doesn't really matter if you have a constant time implementation, for example, whereas if you have, so in some sense, we're really embracing the fact that we have stateful signatures in the context of proof of stake, and that dramatically simplifies things.
Okay, yep, that's definitely an advantage.
I have seen also a question in the chat about like if there is implementation in other language of this specification. So I just linked a repo made by Benedict about the signatures. This is made in Rust. And so we basically use the primitives of Plonky 3, especially like the field, the koala bear field used from Plonky 3. So it should be harder to read than the Python spec because this is much more complex and optimization friendly. But yeah, we have this Rust implementation as well.
Just relaying a comment from the chat, Manu from P2P says that he really likes the tooling that was put in place by Felipe, and it closely mirrors what they have. So that's a great signal.
Yeah. And all of this spec is quite new, so please don't hesitate to put any comment in the repo, open any issues, contact me in DM or anything. Like I would be more than happy to have new best practice or new test or anything that could be relevant. Of course, I will take, or even like opening a peer on the repo, I will review and merge for sure.
And Manu's also asking for, I guess, links to the literature and the resources. And we have plenty of write-ups and content. And we also have a previous call, leanConsensus call, dedicated to the research around post-quantum signatures.
Yeah, if you want, what I can do is that to avoid that being lost there in the channel, I can post that in the Telegram group afterwards. Like we have a bunch of literatures, papers, notes, repo and stuff. So I can put everything in the Telegram group.
Pafar is asking, by role, do you mean regular validator versus aggregator? I actually meant in the context of leanConsensus, where a single part of the idea with rainbow staking is to get rid of the notion of the validator and unbundle it. Instead, we kind of start with a notion of just a staker, and then the staker can opt in to various roles as they see fit. And the three main ones would be attester, proposer, and includer. Includers in the context of fossil and inclusion lists for censorship resistance.
And I think that it is enough that kind of 10% of the global validators opt in to be aggregators. They will, at the beginning of the talk, you mentioned that validators could run on the Raspberry Pi Picoder, and the aggregators will just have to have like a MacBook Pro or like a modern CPU to do the job of aggregation and being able to run the proof on their computer, right?
Exactly, yes. Okay, thank you so much, Thomas. Next up, we have Emile, who will be talking about the virtual machine that he's been actively working on.
Hello, everyone. Can you see my screen?
Yes.
Amazing. So please don't hesitate to interrupt me at any time. I'm not always very clear. So today I'm going to talk to you about this famous minimal zk virtual machine for leanEthereum. Just to recall, what do we want? Why do we need this zkVM? First, to aggregate XMSS, and second, to aggregate those already aggregated signatures, which basically comes down to recursion. Here you can find a list of all the very interesting papers my talk is based on. If you have time, don't hesitate to read them. First, as a building block for this minimal zkVM, we are going to need a way to prove validity of R constraints. So very quickly, what is an R table? You have a bunch of columns that you fill with field elements, and you have multivariate polynomials that must vanish equals to 0 at each transition between two consecutive rows of your table. Traditionally, R tables were proven using univariate PCS, FRI, using quotienting and often using a big field. And I think it might be relevant for us to move to the multilinear paradigm. So replacing FRI with the WIR PCS, which offers lighter proofs, to replace the quotienting with a sum check based approach, zero check, and to replace the big field with the paradigm of small field, big field, like base field, extension field. And as Thomas mentioned, koala bear field is a very promising candidate for us. Here, I'm going to present quickly one way to prove validity of R constraints using this setting, this multilinear sum check based setting. And you can see this as like multilinear Stark, as simple as that. First, we need to commit to our table. Classically, what you do is that you commit to each column as an individual, separate, univariate polynomial. Here, in our settings, what we are going to do is that we are going to pack our columns and to interpret the whole thing as a multilinear polynomial and to commit to this multilinear polynomial. To be precise, we interpret it as the evaluation over the Boolean hypercube of a multilinear polynomial M. So when you have encoded your Airtable, you can commit to it. And then I'm going to describe a simple concept. To each column, I associate up and down columns, so two different columns. The up column is almost identical to the original column, except at the end. The down column, as its name suggests, I shift everything by 1. So instead of starting at A0, it starts at A1, A2, and so on. I just skipped A0. And the key idea here is that if the verifier has access to the original column A, I can give access to the verifier to the A up and A down column using a sum check. You can reduce evaluations on A up and A down to evaluations on A using a simple sum check. Using this fact, we are going to prove validity of one R constraint. So as I said in the beginning, one R constraint is simply a multivariate polynomial in 2 times the number of columns in your table. And this constraint is valid if it vanishes at each transition of our R table. And more precisely, for all the B, n equals the logarithmic, the log of the number of rows in our table, you must have this polynomial equals 0, where I have reused the notation up and down column. And this equality to 0 can be reduced with high probability, meaning cryptographic probability, to this sum equals 0, where we have sampled a random challenge R. And in the end, what you will do is that you will simply run a sum check for this, and you will reduce the validity of your whole R table to a sum check. You execute it, and at the end of your sum check, the verifier will need to access some evaluations of A up, A down, B up, B down, etc. at some random point here. And using what we have seen here, we can reduce the evaluations of the up and down columns to the evaluation on the original columns with, again, a sum check. And so we are here, and at this point, the prover can send the claimed values on each separate column. So for now, these values are claimed, but turns out the verifier can mix them with some randomness, alpha and alpha prime, and reduce the validity of those 4 evaluations to a single claim on our multilinear polynomial M. And so in the end, what we've done is that we have reduced the validity of our R table to a single evaluation on the multilinear that encodes the table M, the table itself. And just as a parenthesis, obviously, if there are more than one R constraint, you can batch them using a random challenge alpha. And one subtlety here is that if you want to get great performances on this 0 check, you will need to probably use a trick to avoid suffering from the embedding overhead that appear in the sum check. Because in the first round of a sum check, you are in the base field, but starting from the second round, you are in the extension field, where all the operations are costly. And there are a few techniques to tackle this issue, but one way to do it, for instance, is to use the univariate skip by Angus Green. And just to give you an idea of how simple this approach here is, a few months ago, there was this Python verifier in less than 500 lines of code. It's really a proof of concept. It doesn't really work and so on, but the main ideas are here. And just to show you that it's possible to implement what I have presented in really a small number of lines and very few Python files. It's pretty straightforward. Now we have this building block which is able to prove validity of Airtable, and we can begin the hard stuff, which is to design this minimal zk virtual machine. So here I have written down the list of most of the complicated operations that our zk virtual machine must perform. Obviously, first the XMSS aggregation and then the recursion. Obviously, a great source of inspiration is the Cairo paper. I encourage everyone to read part of it. It's really interesting. And here, the thesis is probably to avoid relying on too much precompiles. When I say precompile, I mean custom circuits, or in Cairo, they call it built-ins. And to avoid relying on too much precompiles, because a few precompiles equal simplicity, equal security, as always. And I believe it's possible to take inspiration from Cairo, but to slightly change some part of it. For instance, I believe it's possible to remove the allocation pointer. Let me explain. In Cairo, there are three registers: FP, frame pointer, PC, program counter, and AP, allocation pointer. FP points to the beginning of the current stack in memory, the current frame of where we are in memory. PC naturally points to the current instruction being executed in the bytecode. And in Cairo, AP was a register used to point to the frontier, the limit in memory of the region which is which has not been used yet in memory. And in the next slides, I will explain how it's possible to program complex to have complex programs with this without relying on this AP register. And when it comes to the memory, I believe probably as Cairo, a read-only memory is the most simple and efficient approach for what we are trying to build. And in the memory, there will be two parts. This public memory part here is set by the verifier itself. For instance, when the verifier wants to verify the correct execution of a given program, if this program has some parameters, some inputs, these parameters will be written down in this public memory, and the rest is committed, and this is where the execution, the rest of the execution takes place. I believe it's possible to have a pretty decent ISA using only 4 basic instructions that I'm going to describe. As in Cairo, we obviously need to be able to addition and to add and multiply elements of our memory. So add and mul. We also want probably this dereference instruction, which basically lets you access some other frame in memory. Because as you can see, when you add and mul, everything is as offsets relative to the current frame pointer. So you have to imagine that when at some point in the execution, you have your frame pointer that points to the start of your current frame. You perform operations relatively to this frame pointer. But if you want to access some data in another frame, for instance, to call a function, you will need this dereference instruction. We will come back to this later. And finally, a jump instruction, which is a conditional jump, which enables naturally to have conditions, functions, loops, and so on. And note that when you jump, you have the possibility or not to modify the current frame pointer. You can keep it like it's currently, or you can update it with a new value. This is crucial in order to have efficient functions. We will probably also need precompiles, for instance, for the hashes, because both XMSS aggregation and recursion will involve a bunch of hashes. And so at least 2 precompiles, one for Poseidon over 16 feed elements and one for Poseidon over 24 feed elements. And while implementing the recursion program, it turned out that we probably would need a few additional precompiles for recursion. And for instance, one .product precompile to perform like an inner product, but in the extension field, because most of the recursion operation happen in the extension field. And one multilinear evaluation precompiles that lets you interpret a chunk of memory as a multilinear polynomial with coefficients in the base field and to evaluate it at a point in the extension field. Note that this last precompile, using a trick, it's possible to implement it at almost no conceptual cost and no proving time cost. Here is a quick overview of a possible architecture for this minimal zk virtual machine. So you have the memory below. I didn't represent the bytecode because I assume the verifier has access to the bytecode, which is probably the case in our context. And apart from the memory, there are a bunch of R tables, one for execution and 3 for the precompiles. Each R table has a lookup into the memory, which is with logupstar. I will come back to this later. And finally, there is this grand product argument that with fingerprinting and zkR in order to ensure consistency between all the precompiles and the execution calls. Note that in each R table, some columns are not committed. They are virtual thanks to our lookup logupstar. I will come back to this later. Here we are going to zoom a bit on the execution table. So I will need to explain what does logupstar provide to us. Logupstar is an indexed lookup argument recently developed by Lev Sukhanov. And contrary to previous lookups arguments, you only need to commit to the index column to the table containing the data column, but you don't need to commit to the column where you have the data corresponding to each index. So the accessed values by the indexes, you can omit this commitment. You can skip this commitment. And actually, it will save a lot in terms of commitment cost. Because, for instance, in Cairo, at each cycle, you need to fetch the instruction, the opcode, and to decompose it into a bunch of Boolean flags and offsets, actually 15 flags and 3 offsets. And so you need to commit to 18 feed elements per cycle in Cairo. But one other alternative would be to interpret this as an indexed lookup from the program counter column into the bytecode. And doing so, you can completely avoid committing to these 18 feed elements. You simply commit to the PC column here, and all the flags and offsets that comes from the decomposition of your instruction are not committed. They are virtual columns thanks to this logupstar lookup into the bytecode. Same thing for the values accessed into the memory of our virtual machine. You only commit to the indexes do not commit to the accessed values here. And in the end, you get an execution table where you only commit to 5 feed elements per cycle, PC, FP, and 3 memory indexes. And this is much less than Kero, but the drawback of this current situation is that the air constraints have degree 5, which is more than in Kero, for instance. This design, this is currently designed like this because early experiments have shown that the commitment costs were probably the bottleneck. I know it's not always the case for some VMs. For instance, I was told recently that for SP1, it's not the case on their big GPUs, but early experiments on CPUs, because everything here is on CPU, showed that the bottleneck was probably commitment costs. And that's why this Airtable for execution has been optimized to the extreme to commit to a really low number of feed elements per cycle. But if the commitment cost turns out not to be the bottleneck, we can always decrease the degree of our air constraints by committing to auxiliary columns. Okay, so
Emile, we have
that...
a couple of questions in the
yes.
chat.
Yes.
One is, why do we have 2 variants of Poseidon with 16 and 24 field?
A very good question. I will answer it. Typically, when I will take as example XMSS. In XMSS, you first do a lot of hashes for the chains. You have this 64 chain hashes. And for this, you want Poseidon over 16 feed elements because it's more efficient than Poseidon over 24. But once you have done these 64 hash chains, you get the Winternitz one-time signature public key, which is the top of each hash chain. And you need to verify the ownership of this Watts public key to the Merkle tree, because you know the root of the Merkle tree, which is the XMSS public key. And doing so, you need to hash a bunch of, so you need to hash the Watts public key. And if I rephrase, you need to hash a lot of data. And when you need to hash a lot of data, you probably want to use Poseidon over 24 feed elements because you will hash 2 times more data at each time you apply your permutation. Because each time you apply, you need to keep 8 feed elements to keep the previous information, and you have 16 feed elements that you can incorporate from the slice you want to hash. So you need 2 times less hashes using Poseidon over 24 feed elements.
Have you considered using a tree hash rather than, so what you just said was for a sponge, is that right?
Well,
Sorry?
we use sponges to hash really long data, but for a tree, when you have a tree, it's enough if you have hash like 512 into 256. And for this, it's enough to have Poseidon 16, because in the compression mode, when you just feed back the input to the output, you don't have to use sponge. You just kind of put all the input into 512 bits, then apply the permutation, then you store the input to the output, and then you're done.
I understand, but I was suggesting using a tree hash for the long data as well, because then you no, you have a permutation as your primitive, so that if you had a 2-to-1 hash, then you could use that, but that's not what you have. Okay,
I think it still be less efficient than the sponge.
Yeah, it will be. Yeah, you could consider other hashing modes.
The other question / comment has to do with complexity. So if we avoid precompiles, do we have complexity elsewhere, for example, in the compiler or elsewhere?
No, precompiles are only here for performance. Actually, implementing Poseidon without precompile would be quite difficult, but for the 2 precompiles like dot product and multilinear evaluation, it's only for performance.
No, I think Were you talking about my question? So the
Yes.
intent of the question was the other way around. Can you do without a VM at all? So just using precompilers and essentially using a custom circuit.
Yes, so you mean no VM and one big custom circuit?
Yes, in the style of, say, Orchard or Sapling.
Yes, it could probably be possible indeed. It's totally possible. Just I would think the trade-off is the conceptual simplicity, because intuitively it's probably easier to implement this with some kind of programming language and so on than with a pure arithmetic circuit. But I think it could build
I mean, true, but high-level programming languages can compile to circuits.
Sorry?
High-level programming languages can be compiled to circuits, especially if they're tailored for that use. But yeah, it's a perfectly valid approach what you do.
I mean, one thing we're seeing in practice is that all of the commercial zkVMs, SP1, RIS0, etc., they've implemented a minimal zkVM specifically to do the recursion, and just designing this circuit would be very, very difficult, or maybe relies on fancy compilers, which is something we haven't really explored.
I mean, I can't really contradict that, because that's one of the reasons that we haven't used recursion in Zcash yet, even though Halo 2 is designed to support it. And yeah, it's just the complexity of writing the recursion circuit.
Interesting.
So, fair point.
The other kind of stretch goal for all of this is potentially to have this end-to-end formally verified minimal zkVM that can cater for other use cases. So for example, there's aggregation of signatures at the application layer. For example, Falcon could also be aggregated potentially. We have this notion called a privacy wormhole, which is basically having privacy at L1, similar to Zcash. And here you would need to prove that you sent your funds to an unspendable address. And we could potentially reuse the zkVM for that. And if we do a really good job, maybe other blockchains and ecosystems could also reuse the zkVM. So for example, Bitcoin is going to need some form of signature aggregation, because today it can do 3 transactions a second. If the signatures are 10 times larger, it will only be able to do 0.3 transactions per second. And so I think it's plausible that they will either increase the block size or have some form of aggregation. And we're doing all of the heavy lifting to design something which is Bitcoiner friendly in some sense, right? Maximally simple and end-to-end verified.
Are there other questions? Okay,
Nope.
I will continue. I continue a bit. Okay. So just to give you an intuition of how it's possible to program complex functions with this minimalistic ISA. First, as you may have noticed here, in the instruction, jump requires a Boolean condition. This is again used to save commit to avoid committing to an auxiliary column in the R. But we can reduce conditions that are not necessarily Booleans into a Boolean one using only 3 cycles. So here I described it. And using it, we can do conditions, like we can design a high-level language and a compiler, which naturally with blocks, and you can jump to the appropriate block depending on the condition. But more interestingly, it's how do you design functions? Because you don't have the IP register. And this is the key reason on why I think we can remove this IP register. Let's say you are here in this yellow frame, and you want to call a function, my function, that takes as argument y. So first you need to know at at compile time, first the bytecode address of the function, so where the function lies in the bytecode, and two, the memory footprint of the function, which is what is the size of the frame I need to allocate when calling this function, my function of y. And the key idea is that when executing the program, you will receive as a hint a pointer to a newly allocated frame. So the prover who is running the program and generating the proof will keep track of the AP register in order to be able to hint correctly new allocated frames where the function will execute. But from the verifier point of view, there is no need to keep track of this AP register because you do not really care where this new frame will be placed because we are using a read-only memory. And so there is no risk of overwriting previously written memory with this new function call. And so what you will do is that you will use here the dereference instruction to write down at the beginning of your new frame your current program counter and frame pointer, your argument that you want to call the function with, and in the end of the my function call, you will be able to jump back to the yellow frame, to the previous context, using these PC and FP values that have been inserted at the beginning of this green frame. And that's the key idea. You can, I believe, remove the AP register and using a hint because it's a read-only memory. That's it. Now you can do loops. If the number of iterations is known at compile time, I would suggest for performance reasons to unroll the loop. And if not, you can rely on a compiler that will transform each loop into a recursive function. And this allows for loops with an arbitrary number of iterations. As a conclusion, what has been implemented and what needs to be done? A compiler has been implemented with the compiler is not really stable and mature, but has some complex features like inlining, loop unrolling, function, obviously, condition, matches, constant arguments, etc., etc. The zk virtual machine that has been presented here has been implemented in a feature-complete way. The code is not mature at all, but at least it exists. Using both items, a weird recursive program has been implemented. So a program using these 4 primitive instructions and the 4 precompiles that can prove when we're opening, and it works. And finally, the XMSS verification program, but unfortunately, as Dmitry and Thomas said, currently in its current form, it does not rely on the real encoding top of the hypercube. More work is necessary to include this encoding. It's not as trivial because it's a bit complicated to make it efficient with this ISA. What needs to be done is so to include this top of the hypercube encoding. 1, 2, to finish the recursion program. Currently, we only have weird verification, which is a big part of the recursive proof, but it's not all. And more importantly, to improve performance. Just to give you a number, currently in its non-optimized form, the VM is able to perform recursion in a weird verification. So big part of the recursion in 2.7 seconds. And what we need is obviously something at least 10 times faster. But as I said, the VM is in its current form not optimized at all. And so there is a lot of room for improvement. That's it. Thank you.
Thank you, Emile. Fantastic presentation as well, and super impressive that you came up with all of these improvements over the Cairo design. Actually, I'd be curious to get your sense, like if you were to take Cairo as it is today and implement all of the optimizations, kind of move to multilinear and sum check and were, and remove the AP register and implement log-up star, like how much faster do you think you could make Cairo?
Honestly, I don't want. It's too hard as a question. I don't know, honestly. It's very hard.
That's fair.
I don't know Cairo enough. But if there are Cairo people in this Zoom, I would be really interested of one figure, which is what is the time of on a standard laptop to do one recursive proof on Cairo. And it would be really interesting to know. Because we can compare, for instance, in its non-optimized way, recursion currently costs a few seconds. And so we can compare with the time Cairo, with the time Cairo need for recursion on a standard laptop. Yeah.
I was going to ask, what's the bottleneck there?
There are a lot of bottlenecks.
Okay,
First,
it's not just one bottleneck, yeah.
No, it's for instance, this figure of 2.7 seconds has been implemented, has been benchmarked on a degree 8 extension of Koala Bear. And currently there is a work in progress to transition into a smaller extension, degree 5 or 6 of Koala Bear. And so we will get direct improvements in terms of performance simply using a smaller extension field. But there is like 10 to-dos that will improve performance.
Thank you.
Divya asks, does a recursive function in this context use tail recursion?
Use what, sorry?
Tail recursion.
I don't know what it is. Sorry.
Yeah, in the sense that like the call instruction is immediately followed by the write instruction. So it's like recursive.
The call from by the right?
Yeah.
By the return instruction. I guess there is no explicit return instruction.
Yes.
I see.
Okay, sorry. There is no explicit return instruction indeed, but there is some kind of return using this jump. When you want to call a function, before jumping to the new frame, you write at the beginning of the new frame your current program counter and frame pointer, and so then you jump, and so at the end of this new function, you are able to return by jumping back on your previous context.
I see. Okay.
I mean, so if you compile into jump instructions, then you can directly implement iteration. You don't necessarily have to go via recursive functions.
Yes.
Which means that a compiler has everything it needs to transform the recursive functions into iterative ones, like a normal optimizing compiler does for tail recursion.
Okay, well, we're out of questions and it's perfect timing because we're just at the hour. Congratulations to the 50 people who made it through 2 hours of content, and looking forward to seeing you all on call number 8. Thank you so much to all the speakers and have a great weekend. Bye, everyone.
Thanks a lot.
Thanks, bye.
Bye.